In our last video, we left off talking about parallel lines and perpendicular lines. So let's just quickly review what those are. So parallel lines are lines that never cross, right? They never intersect. Parallel lines, think of two runners, okay? And the first runner, runner A, starts a race, and runner B starts the race a little bit later. Now, if they run at the same speed during the whole race, then runner B will never catch up to runner A, right? Because they're running at the same speed and runner A starts before runner B. So it's something similar with parallel lines. They have the same slope. They're increasing at the same rate. So because they're increasing at the same rate, and let's say one line is a little bit above another line, these lines are actually never going to meet. Whereas if one line had a slope that was greater, then it means it's increasing at a faster rate than the other one, and eventually they catch up to each other. So you can see here that the slopes of parallel lines are going to be the same, so that they never meet. Perpendicular lines are a little bit different. So perpendicular lines are lines that intersect specifically at a 90-degree angle, and they have slopes that are negative reciprocals of one another. What does this mean? This means that if the slope of the original line is 3/4, then when we look at the slope of the perpendicular line, we flip the fraction, okay? So the 3/4 becomes 4/3, and the sign changes. So if it was positive, it becomes negative. If it was negative, it becomes positive. So -2/3, when we flip it, it becomes 3/2, and it was negative, so we have a positive 3/2. For whole numbers, remember every whole number could be written as a fraction. So 4 is really 4/1. So when we flip it, it becomes 1/4. And then the 4 was positive, so the slope of the perpendicular line is going to be negative. And then the same thing with the -1/2, right? When we flip it, it's 2/1, but you don't want to write a whole number as a fraction, right? If you can help it, don't write it as a fraction. So it just becomes 2, and it was a -1/2, so this is going to be a positive 2. Okay, so let's talk about how this affects us. So let's just take a bunch of examples of when this might come up. So given, let's say y equals 3x minus 4, let's write the equation of a perpendicular line. And I'm going to abbreviate perpendicular with this symbol, okay? It looks like an upside down T. That means perpendicular. If you remember, we talked about that in the last video, okay? So we're going to find the equation of a perpendicular line that passes through the point 6, 2. Okay? Okay, so we have to write an equation of a line, and there are 3 different ways to do that, right? There's point-slope form, there's slope-intercept form, and there's standard form. Now, when you do a problem like this, you're never going to do standard form, okay? You're only going to use point-slope or slope-intercept. And in most cases, you're going to use point slope. Why are we using point slope? Because that's what we're given. We're given the point, okay? So here's our point. This is the point that we're given. And we're also actually given the slope. And the slope comes from this line that we're given here, y equals 3x minus 4. So this line that you're given, you're going to use this to find the slope. That's the only thing that you use this for. After that, it becomes irrelevant. okay? So let's actually work through this. And it's a very short process, okay? Because essentially all we have to do is find the slope. And this is very fortunately given to us in slope-intercept form. So it's easy to find the slope, okay? The slope, because this is in slope-intercept form, remember y equals mx plus b. The m is the slope. 3 is our slope here. So the slope of our line is 3. But this says that we need to write the equation of a perpendicular line. So now that we have the slope of the line, of the original line, we need the slope of the perpendicular line. And the slope of the perpendicular line is the negative reciprocal. So this was 3, right? This was 3. So when we flip the fraction, it becomes 1 over 3. And this was positive, so our new slope is negative. Okay, so now we have the slope and the point. So we're going to use point-slope form. And this is very typical. You're rarely given the y-intercept. You're usually given a point. So when you go and you start writing your first equation, it's almost always going to be point-slope form. So if you remember, and you should consider pausing the video and try and write the equation yourself. It's y minus our y1. So our point is 6, 2. So our y1 is 2. Is equal to our slope times x minus x1. And our x1 is 6. And this is it. It doesn't tell you what form to put the equation of the new line in, right? It doesn't say that your answer has to be in standard form or slope-intercept form. So you're done here, okay? You don't have to do anything else. Let's take another example. And this one I'd like you to try on your own. I apologize for all the background noise. So we're going to do a perpendicular line again. And if you notice, I'm starting to leave out a couple of words just to save some time, but we're saying passes through the point. Okay. So we have our two things again. We have our point. It's given to us. This is the point. And we have the equation that we're going to use to find the slope. This is all that we use it for. Once we find the slope, this becomes irrelevant. Okay, that's really important because a very common mistake is that people, once they find the slope, somehow they start using this equation again. This equation is completely irrelevant once you find the slope. The thing that you're going to do is you're going to use this point-slope form, and you're using the point and you're using the slope that you found from this equation. So my suggestion might even be that once you find your slope, you cross that out. You say, okay, I don't really need this anymore. Okay. Okay, so now we have this 3x plus 6y equals 18. And just like before, the first thing that we have to do is find the slope, because then we can put our equation in point-slope form. Okay. We know that for any equation that we use, we have to find the slope. So here's the thing. This is in standard form, right? And we need to find the slope. So to find the slope when our equation is in standard form, we're going to convert it to y-intercept form. So this is just a little bit more work. Not a lot, but a little bit. Okay. So I'll write this out for this one. If the equation given is in standard form, to find the slope, you have to convert to slope-intercept form. Because remember, standard form there's nothing in there that directly gives us the slope. So we have 3x plus 6y is equal to 18. Okay. Remember that to convert to slope-intercept form, we solve for y. So we have to subtract 3x from both sides. Okay. That's going to give us 6y is equal to negative 3x plus 18. And then we have to divide everything by 6. And remember, when you're converting to slope-intercept form, when you divide everything by 6, actually take the negative 3x and divide it by 6, and take the 18 and divide it by 6 separately, okay? And what we get here is y is equal to negative 1/2 x plus 3. So now it's in slope-intercept form. So the slope of our line is our negative 1/2, but we need the slope of the perpendicular line because we're looking for the equation of a perpendicular line. If this had said given this, write the equation of a parallel line, then we wouldn't have to do anything with this. This would be our slope, okay? The slope of the perpendicular, we flip the fraction, so 1/2 becomes 2/1. And this is negative, so our new slope is positive. So it's just a positive 2, okay? And our point is given to us. Our point is negative 1,7. So now we're going to put it in point-slope form. So we have y. The y value of our point is 7. So we do y minus 7. Then we have our slope, which is 2. And then we have x. And the x value of our point is negative 1. So x minus negative 1 becomes x plus 1. Okay. So this is the equation of our line. And again, we don't have to do anything with it because it didn't specify that we need it in any specific type of form. Okay. It said that we need it in, if it said that we need it in slope-intercept form, then we would go and we would have to convert this to slope-intercept. If it said that we needed it in standard form, then we would have to go and convert this to standard form, which is what we did last time, okay? Let's do one more, and then we'll move on. Let's say y minus 6 is equal to negative 2/5 times x plus 3 Let's write the equation of a parallel line. So remember, the symbol for parallel is two lines next to each other. This time we'll say that it passes through the point 3, comma, negative 2. And we'll add an extra piece. We'll say and put in standard form. So you get a little bit more practice with that. And nothing changes here, okay? You still need to find, we have the point, okay? So we know that we're going to be starting in point slope form, and we just need to find the slope. So the slope of our line we can find this as point slope form. We recognize this as point slope form because it's not solved for y and it's not solved for constants. That should indicate that it's point slope form. And we know that the slope is written outside the parentheses, so the slope of our line is -2/5, right? Which means that the slope of our parallel line is also -2/5, okay? Again, we're doing parallel this time, so the slopes are the same. Now we know that our point is 3, -2. At this point, you should definitely be pausing the video and trying to do the rest of this yourself, okay? So we're going to start by putting the line in point slope form because we have the point and the slope. So we have y. The y value in our point is -2, so y minus -2 becomes y plus 2. Then we have -2/5 times x, and then the x value is 3, so it's x minus 3. Okay, so at this point, we have to put this in standard form. And we have two options here. We can start by getting rid of the fraction, which just means multiplying the whole equation by 5. Now, some of you may struggle with this because you have this set of parentheses, okay? If you multiply the whole equation by 5 at this point, then this side of the equation, the right side, actually doesn't change except we get rid of this 5, okay? Because this is being multiplied. And when we multiply the whole thing by 5, you have -2/5 times x minus 3 times 5. So the 5s just go away. You're not distributing anything, okay? And then on this side, you would have 5y plus 10. Now I'm going to do it a little bit differently. I'm going to distribute first. I'm going to get rid of the parentheses first. And the reason I'm doing that is because I think that you're less likely to make mistakes. And this just has to do with how much experience you have working with equations and getting rid of fractions. And if you're new to this, if this is the first time that you've seen this, then you may want to do your distribution first, okay? So if we distribute the -2/5 first, which does not make this any harder, by the way. Eventually you're going to have to distribute, so it doesn't make any difference. That's going to give us y plus 2 is equal to -2/5 x. And then remember, this is a 3/1, so we get plus 6/5. Only the numerators get multiplied. It's not that. It's that the denominator is 1. So 2 times 3 is 6, and 5 times this invisible 1 is 5. Now this looks a little more familiar. We know how to do this. We know that to get rid of the denominators, we multiply by the lowest common denominator, the lowest common multiple. And there's only one denominator, so it's easy. We know that we're multiplying everything by 5. Okay, and we have to distribute that 5 to everything. Do not forget that. Too many people forget to distribute it to both sides. Okay, and the whole point of this is to get rid of your fractions. So if this does not get rid of your fractions, then you multiply by the wrong number. So here we get 5y plus 10. And our denominators just disappear. We get -2x plus 6. Okay, and again, if you're not that comfortable with canceling, this becomes -10/5 when you multiply, which is 2, and 30/5, which when you reduce, it gives you 6. And remember, that's because this is a 5/1. Okay. Okay, now from here, we just need to get this in standard form, okay? And keep in mind that we're getting rid of our fractions because in standard form, you're not allowed to have any fractions. So in standard form, our x's and our y's are on one side and our number is on the other, which means that this 2x has to move over to the left and this 10 has to be moved over to the right. Okay, so if we're moving the 2x over to the left, we have to add it to both sides. And again, we can do this in one step. You can do it in two. We need to subtract the 10 from both sides. Notice that the 10 goes away on the right and the 2x goes away, the 10 goes away on the left and the 2x goes away on the right. So what are we left with? 2x plus 5y is equal to -4. Okay, so everything that we did was exactly the same. We used the original line to find the slope. Once we used that to find the slope, we ignored this. This was irrelevant, okay? It's a totally different line now. We used the slope of the parallel line and the point to put our equation in point-slope form. Once we did that, we just went back to all of the things that we did in the last video and we took this and converted it to standard form. Okay, so we distributed the -2/5. That got rid of the parentheses. Then we got rid of the denominators by multiplying by 5. And then we got the x's and y's over to the left, and we got the number over to the right. Okay. Okay, so that's it for this. So the next thing that I want to talk about is just how to graph a basic line, one line. Okay, so let's take, and I'm actually only going to do one example of this because it is pretty straightforward. I'm just going to point out all of the pitfalls as we go. Okay. Now, when you graph a line, you can always, you can put it, you can just plug in an x value, solve for the y, and you get a coordinate. And once you have two coordinates, you're done, okay? You just connect the 2 points. So you only need 2 points to graph a line. If you don't want to choose just any point, usually the easiest points to choose are where it goes on the axis, okay? Where it intersects the x-axis and where it intersects the y-axis. So that's what we're going to do to graph the line, but just know that this is not the only way. You can also use the slope. If you have point-slope form, then you have a point, you have the slope, and you can use that, right? We could say, okay, well, this line starts at 3, -2, and we know that as we go to the right by 5, we go down by 2. So another point on the line, well, going to the right by 5 would make this an 8, and going down by 2 would make it a -4, okay? So, and we got that from the slope here. Remember what we said about slope. We go to the right by the bottom number, and we go up or down by the top number, depending on whether it's positive or negative. So this is negative, so we go down. So if we have 3, -2, when we go to the right by 5, we're adding to the x, so we get an 8. When we go down by 2, we're subtracting from the y, so we get -4. So then we just plot the points 3, -2, and 8, -4. And once we do that, we connect the dots, okay? So 2 points to make a line. So if it's in point-slope form, you could do that. Slope-intercept form, you can do the same thing. You have 1 point because you have the y-intercept, and you can use the slope to get at the second point. Or you could plug in any x value. Find the y value. Do that twice. So plug in x equals 1. See what you get for y. Okay? It's a little bit more work because you're solving the equation for y. Okay? And it's possible that you might get a fraction, which could make it a little bit harder to graph. It's not a big deal, but it's just something extra to think about. But this is another way. And you can do this with any line, which is why you can do it with a line in standard form, in point-slope form, or slope-intercept form, which is why I'm going to show you this way. Okay? So let's take an example. Let's say that we have y. Sorry, I did not write that correctly. That's not what I meant. Let's say that we have, let's take the 3x plus 6y is equal to 18. Okay, so we're going to graph it. So one way to do this is to start by finding the intercepts. So let's say that we start by finding the x-intercept. Remember, the x-intercept is where it intersects the x-axis, okay? At the x-axis, our y is equal to 0, okay? So when we do this, what this means is we're going to plug in 0 for y. And some of you will be able to skip the step altogether, one of these two steps. But you get 3x is equal to 18. And then you get x is equal to 6, because we can just divide both sides by 3, right? So when we have an x value of 6, what that means is, and this is really important, your x-intercept is a point. So don't write x equals 6 as your final answer. Your final answer is 6, 0, okay? And this is the most common pitfall because people forget that this actually gives you a whole point. It gives you an x and a y value, okay? Second thing that we're going to do is we're going to find the y-intercept. This is going to give us the second point. So we get 2 points from this, not 1 point. So the y-intercept is when x equals 0. It's very similar. You're plugging in 0 for x. And again, you can skip one of these two steps. You get 6y equals 18. You don't have to skip these steps. And we know that we divide both sides by 6 to get y by itself, which gives us y equals 3. And again, this is not your whole point. Your whole point is 0, 3. And the reason I mention this is because too many people write this as 1 point. They say, oh, we have the point 6, 3. 6, 3 is not necessarily on this line. We have 6, 0 and 0, 3. Okay? Gives us 2 points. Now we're going to graph the 2 points. Remember, one of the points is going to be on the x-axis and one of the points is going to be on the y-axis. So we're graphing. Now a sketch, when it says sketch, it means that it has to have some accuracy. Okay? So your axes must be labeled. They have to be labeled because we don't always work in the x-y axis. Sometimes we work in other types of axes, which actually you'll see in our next unit when we do, like, for example, complex numbers. But there are lots of different types of axes, and they're not always labeled x and y. So we have to know that we're working in the coordinate plane, okay? And we can plot each point. So we have 6, 0. You don't have to label in a sketch. You don't have to label every one of these tick marks. Okay, so we have our 6, 6, 0 would be over here. That's our first point. That's our x-intercept. Then we have 0, 3. So that's our next one. And now we just connect the dots. And I would label your line. So this line is 3x plus 6y is equal to 18. Okay? So we connect the dots and label the line. This is what would be considered a sketch. It's not okay just to draw a random line. You have to show the points that it goes through. Okay. So I'm not going to do another one of these. I think this is a small point because there's so many different ways to graph the line. And we'll be doing more of this when we do the piecewise functions in just a minute. Okay. So just remember that this is one way to do it. You just find the x-intercept by plugging in y equals 0. Make sure that when you're done, you actually write it as a point so that you don't make a careless mistake. Then you're going to find the y-intercept by plugging in x equals 0, and you just solve for y. Okay. Plot your points. So put them on the graph, 3, 0, 0, 3, and 6, 0. Connect your dots, and then label the line, and you're done. Okay. So you're using the intercepts. That's one way to do it, okay? Okay, so let's move on. And if you're tired and you feel like you kind of need a break, this is a great time to take a break. So pause the video, come back to it later if you have to, because we're starting something just a little bit different, okay? Okay, so the next thing that we're going to talk about is something called piecewise functions. So essentially what we're doing is we're taking a function and we're breaking it into small pieces, and each piece is a function, okay? So when we talk about a piecewise function, what we're talking about is a combination of other functions that still results in a function. Our final answer will still be a function. So a combination of functions that results in a function. Okay, and that's really important that our final result is a function as well. So if you think about it on a graph, we could take 3 different linear functions, put them together, and get a function still. So for example, here's what it would look like. And we're going to graph some of these so you'll see what happens when we actually graph it. So we might have this line, combine it with this line, and combine it with this line. This would be considered a piecewise function. We have 3 pieces in this particular piecewise function, right? 3 pieces, 3 separate lines. Here's our first piece. This is our first function. In the middle is our second function. And then on the end is our third function. So we have 3 separate functions. And the result is still a function. If we drew vertical lines through here, we would never cross through the graph more than once, right? This passes the vertical line test. Now, it doesn't have to be 3 pieces. It could be 10 pieces. It could be 2 pieces. Here's another example of a piecewise. We'll look at a 2 piecewise function, 2 pieces. Now this is a 2-piece function. So some of you may be familiar with the quadratic function, a parabola. So we have part of a parabola. This is the parabola. And then we have a line. And when we join them together, it's still, this comes out. It's not a, it's not vertical. So this still passes the vertical line test when we put those functions together. Okay. Let's take one more example of what a piecewise function would look like. Okay, this is an example of a piecewise function with 4 functions. So we have 4 lines. It doesn't always have to be a line, right? We already saw that we could have a parabola. It's just that these are the functions that we're talking about right now. Okay, so we have 4 different functions in this one. But again, if we drew a vertical line anywhere on this graph, it would pass, right? We would pass the vertical line test, which means that the final result, when we put them all together, gives us a function. Notice there is no overlap between the 2 functions, between any of the functions, right? The parabola stops at this wall. It does not keep going, it stops. We're saying the parabola only exists before that wall. After that wall, we only have the line. Okay, so let's talk about a couple of things before we start. First thing is an absolute value function. The graph, this is kind of like a side note. The graph of y equals absolute value of x an absolute value graph bounces off the x-axis. Remember, your y values can never be negative. So hopefully you're able to construct these yourselves, but just in case, right? Whenever you're graphing, you're plugging in a value for x and you're finding what y is equal to. So y equals absolute value of 1. The absolute value of 1 is 1. So that would be our first point. The absolute value of 2 is 2. So this would be our second point. Absolute value of 3 is 3. Absolute value of 4 is 4. Absolute value of 0 is 0. And then it bounces off the x-axis. Okay? What we mean by that is the absolute value of -1 is +1. Absolute value of -2 is +2. Absolute value of -3 is +3. Absolute value of -4 is +4. So an absolute value looks like a V. It bounces off. It bounces off of that x-axis, okay? So you hit the x-axis, it doesn't go through it. Instead, it bounces off like light, okay? Like light would bounce. Okay, so that's just a side note so that you are aware, just in case I decide to use an absolute value function, okay? Okay, so let's take a look at what a piecewise function looks like, and then we'll graph a few. Okay, so a piecewise function is written very much like a regular function. It's just that we write it in pieces. So we would say f of x, I'm going to rewrite this as piecewise so you don't confuse it with the absolute value. F of x equals, and because we're going to have multiple functions, we use that brace again. Okay, and our first function is going to be, let's say, 2x. Our second function we'll say is x plus 1. And we have to say where these functions exist, right? What we're essentially doing is we're saying, where is the wall? Where does the function stop? The first function stop and the new function start. So what we're going to do is we're going to say, okay, well, 2x is for all x values that are less than 2. And that means that x plus 1 is for all x values that are greater than or equal to 2. Okay, and notice they're opposites, right? So we have less than 2, greater than or equal to 2. So this here is our wall. We only have one wall. We have two functions, one wall. Okay, that's where one function starts, one function stops, and the other function starts. Okay. Okay, so let's talk about how to evaluate this function. Okay, so first of all, this is something we haven't talked about, so I hope I haven't confused you. A function, okay, so I'm going to put this as a side note again because I realized we didn't talk about this and you may not know this. So I'm going to put this as a side note over here. So function notation is f of x. X is our input. This is just our x value. And f of x together is our output. And it's just another way of saying y. And the reason why we use this is that if I gave you y equals 3x plus 1 and I said, is it a function? You would have to think about it. You would have to figure out, okay, well, is there one y value for every x? If I plug in an x, will I get only a single y, or will I get multiple y's? Or you might think about the graph and say, okay, well, does y equals 3x plus 1 pass the vertical line test? If we say f of x equals 3x plus 1, what that's doing is it's telling us you don't have to think about whether or not it's a function. I'm telling you it's a function. So the f of x tells us 3x plus 1 is a function. Without us even having to think about it. Because not everything is a function. We know that all lines except for vertical lines are functions, but if you're given other stuff, you don't necessarily know that it's a function, okay? You have to think about it. Here, the f of x tells you don't think about it. It is a function. This tells you when we put these two graphs together, we get a function. You don't have to think about it. You get a function. I've told you that. I've given you that information by writing f of x. Now, the other thing is, if we write something like f of 3, what that's doing is it's saying change your x to 3. Plug in 3. And you will get an answer. So we get 10. Okay? So this tells you plug in 3. That's how you would read it. So if we wrote f of 5 would tell you plug in 5. And 3 times 5 plus 1 is 16. So this number in the middle is saying what your x is equal to. Okay, so this is our little side note. And I'll box it off. Okay, so before we think about graphing a piecewise function, let's just evaluate a piecewise function. We're going to evaluate a bunch of different piecewise function, a bunch of different values. Okay, so we're going to figure out what y is given all different x values. So based on this function here, so notice this is a side note now, we're moving on. Okay, let's find f of 0. Now what this is doing is it's saying plug in 0, right? But we have to know which function to plug 0 into. So the other thing that this tells us is this tells us what function to plug into. That's the second thing that this tells us. Okay, because it's telling us, well, if our x is less than 2, then we're going to plug into 2x. If our x is greater than or equal to 2, then we're going to plug into x plus 1. So this says x is equal to 0. And 0 is less than 2. So we plug into the first function. I'm going to say top function. Okay, so do you see what we did here? We said, okay, our x is equal to 0. So we're going to go here. This is going to tell us which of the functions to plug into. So 0, we're going to plug it into each of these. Whichever one it's true for, that's going to tell us which function. So 0 is not greater than or equal to 2. So we don't plug into this one. 0 is less than 2. We plug into 2x. So this is equal to 2 times 0, which is just 0. Okay, let's do another one. Let's say that we have f of 6. So we have to know which function to plug into. Well, is 6 less than 2, or is it greater than or equal to 2? It's not less than 2. It's greater than or equal to 2. So because 6 is greater than or equal to 2, we're going to plug into that second function, that bottom function. Okay, so you only plug into one function. You never plug it into all of them. Some people evaluate all of the y values and then determine which y value to use based on this. No, you will only get one y value, okay? So this will tell you where to plug in. Let's say that we had f of 2. So 2 is greater than or equal to 2. It's not less than 2. So that tells us plug into the second function. So we have 2 plus 1 is 3. So f of 2 is equal to 3, which means we have points here, okay? The point 0, 0. Remember, this is our x, this is our y. F of 0 is our y. This point, the x was 6, The y that we got was 7. It gives us a point. Here, the x was 2, and the y that we got was 3. So we got the 2 from here. This is our x, right? X equals 0, x equals 6, x equals 2. The result is the y. Let's do one more from this function. Let's do f of negative 11. So you're going to go over here and you're going to say, okay, is negative 11 less than 2 or is it greater than or equal to 2? Negative 11 is less than 2, which means that you plug into that top function. So 2 times negative 11. That gives us negative 22. Okay, and that gives us a point. Our x value was negative 11. And our y value was negative 22. Okay, let's do a different function, and then we'll graph. Let's say that we have f of x is equal to, we'll do 3 functions this time. So let's say that we have negative x minus 2 is our first function. Let's put in x squared. Now, I will not make you graph something that isn't linear right now. So x squared, for those of you who are aware, is quadratic, okay? It's not linear. We know that because the exponent of x is not 1, okay? And let's do absolute value of 3x minus 4. So I wouldn't ask you to graph this, but I would ask you to evaluate y values, okay, based on x values. So you may be asked to do something like this, but you won't be asked to graph. So let's say that negative x minus 2 is when x is less than or equal to negative 5. X squared is when negative 5 is less than x, which is less than or equal to 1. And finally, absolute value of 3x minus 4 is when x is greater than 1. So keep in mind, notice that these numbers match, right? We have 2 walls here. And this becomes important when we start graphing. One wall is at 1, the other wall is at negative 5. This tells us our walls. Remember that the walls are when one function ends and another begins. So the top function ends at negative 5, and then we start doing x squared. Okay, remember that those walls are what we were talking about here. Okay, so it's 3 functions put together, which means that we have 2 walls. First function stops, second one begins, second function stops, third one begins. Okay, so let's just do some evaluating, not graphing yet. Let's say that we want to know what f of zero is. Okay, well, we go here to figure out which function. We have to say, well, where is 0? Is it less than or equal to negative 5? No, so we don't plug into the first function. Is it between negative 5 and 1? Yes, 0 is between negative 5 and 1. Okay, this is saying 0 is between negative 5 and 1. So we plug into the middle function. So we're going to plug 0 into x squared. Which just gives us 0, which means that the point that we have is 0, 0. Okay, and you don't need to necessarily write out the point if you're just being asked to evaluate, but I'm preparing you for the graphing, okay? Okay, let's do another one. Let's say that we have f of 6. So again, we go here to figure out what we plug it into. Well, 6 is not less than or equal to -5. It's not between -5 and 1. 6 is greater than 1, and it can only satisfy one of these, okay? You're never going to be saying, oh, wait, 2 of these are true. That won't ever be the case, okay? So 6 is greater than 1. That tells us we plug into the bottom function. So notice you're figuring out what function you're plugging into first. So we have absolute value of 3 times 6 minus 4. That's the absolute value of 18 minus 4, which is the absolute value of 14, which is 14. Okay, you don't have to do every single step here, but I put it in so that you understand where we're getting stuff from. Okay? Okay, let's write our point. Again, at each of these points, you should be pausing and trying to do it yourself. So the x is 6 and the y is 14. So our point is 6, 14. Okay, let's do another one. Let's say that we have f of -3. Is -3 less than or equal to -5? No. Is -3 between -5 and 1? Yes. So we're plugging into the middle function. So it's -3 squared. Now remember from order of operations, the whole -3, sorry, I should put this in black. The whole -3 is being squared, not just the 3. The -3 is in parentheses. Whole -3 gets squared, which means that 3 gets squared, but so does -1. So this becomes a +9. I apologize for that. And for that, something went weird there. Okay, and then once again, we have our point. The x value was -3, the y value was 9. And let's do one more and then we'll graph. So we have f of -10. So you should pause it, see if you could do it yourself. So -10, we come up here. -10 is less than or equal to -5. So that tells us plug into the top function. So be careful here. This is a common mistake. You are taking the negative of -10. Okay. Take your x and put it in parentheses if you have to help you with this, because a lot of people will miss that second negative. Okay. You're taking the negative of your x. Your x is a negative number. If you take the negative of a negative number, it becomes positive. So you get 8 here. So be careful with that. This is where people get confused. Okay. So our x value is -10 and our y value is 8. Okay, so now you have all the tools to graph a piecewise function. So we're going to graph two of them so that you get practice. One of them we'll do with 2 pieces, one of them we'll do with 3 pieces. The method for graphing is always the same. And we're only going to graph with linear functions. We won't even do absolute value because absolute value, remember, if it hits the x-axis, it bounces off. So you have to be really careful that you don't wind up with anything negative, okay? Okay. So, 2 examples. First example. F of x is equal to negative 2x plus 1, and that will be for any x that is less than negative 1. And then we are going to have x minus 2, and that is going to be for any x that is greater than or equal to negative 1. Okay, so we're going to graph it. First thing that you're going to do is you're going to find your wall. So our wall we find from here, right? This is our wall up here. We have 2 functions, that means 1 wall, and our wall is at negative 1. So I'm going to put an axis down at the bottom because that's where we're going to graph. Hopefully I made it big enough. So the first thing that you're going to do is you're going to mark off your wall. Okay? And when you mark off your wall, it doesn't really, it's invisible. Okay? You're using it to help you. So it doesn't, when you see a piecewise function graph, you don't actually see these lines. Okay? That's there just to help you figure out, okay, to the left of the wall, I'm doing one function. To the right of the wall, I'm doing another function. Now, both of these are linear. On each side of the wall, you're going to have a line, okay? So you're going to graph the top function. First thing that you do to graph the top function is plug in x equals negative 1. Remember, this is your wall. We're plugging in that point, okay? And notice that it's not included, but we have to know where it stops. So in order for this to be a function, the reason why you'll never see less than or equal to and greater than or equal to, right, is because it has to be a function. At x equals negative 1, it can only be one of these. Otherwise, it's not a function. Then there would be 2 points on your wall here, and this vertical line would pass through 2 points. So the reason why you still plug in x equals negative 1, even though you would not be using it, even though it's not a part of the function, is because you need to know where it stops. Negative 1.00000001 is part of this function, but you're not going to plug in negative 1.00001. So we do this with the open and the closed dots, right? So we're going to have an open dot here because this point that we're plotting is not included, okay? You'll see what I mean in a second. So we plug in x equals negative 1. Negative 2 times negative 1 is 2. And we get 3. This gives us a point. Okay. The point, the x, was negative 1, and the y was 3. Now this is on the wall. Now the wall is the only place where you're going to have either an open dot or a closed dot for every function, okay, for the functions that are on that wall. So this function ends at negative 1. This one starts at negative 1. That means that we are going to have this on the wall, but it's an open dot because it's not included. So at negative 1, 3, we have an open dot. Okay, so we're saying that this isn't actually a point on the line, but the function negative 2x plus 1 is going to come up so close to this line that we're saying this will help us figure out exactly where it ends. Okay, so we don't want to, in other words, plugging in negative 2 isn't enough because negative 2 would end the function somewhere over here, and you would be missing all of the points between negative 1 and negative 2. Okay, so the first thing that you do when you graph a function is you always graph the point on the wall, and it's either going to be an open dot or closed dot. Okay, closed dot if it's included, which you'll see in the next one. Okay, now that we've plotted one point, we're going to plug in an x value. And you're going to make sure it's where the function exists. So in this particular case, you have to plug in a point that's less than negative 1. Now you only need 2 points to make a line. So it could be negative 2. That would be fine. It could be negative 3. That would be fine. Okay. So we're going to plug in, let's say x equals negative 3, just to give us a little bit of space. Okay. So if we plug in negative 3, we get negative 2 times negative 3 plus 1. This gives us 6 plus 1, or 7. So the point that we have from here is negative 3, 7. So we're going to plot that. So here's our 7, here's our negative 3. And every other point on this line is closed. You only have one open dot. Your open dots are only along on the walls and only where you don't see equal signs. Okay? You never have an open dot unless it's on the wall. So we have negative 3, 7, closed dot, closed dot. Now we just connect it, and our arrow is facing away from the wall, always. So connect your points, and your arrow always faces away from the wall. Remember, the idea is that you can't go through a wall. It doesn't make sense. Why would you have an arrow that's saying go through the wall? It doesn't make sense. Okay, so your arrow always faces away. So you connect your dots and then you're facing away. And now what you're doing is you're saying, okay, this is the function negative 2x plus 1, and it only exists on the left. Okay. Now we're going to graph the function, the second function, the bottom function. So I'm going to put that in purple. And I'm going to start it here. And you start the same way. You're plugging in x equals negative 1, right? This is the wall. So you always plug in where your wall is. So we plug in negative 1, we get negative 1 minus 2, which is negative 3. So our point here is negative 1, negative 3. And this is closed. And it's closed because it's included. We have a greater than or equal to sign. So it's a closed dot. So we're going to plot it. So we have to get to negative 3. And it's a closed dot that is on the wall. Okay, so notice this vertical line still passes through only one point because this is not really a point that's on the line or on the function. Okay, then we just plug in another point. So plug in an x such that our only requirement is that x is greater than or equal to negative 1. So let's plug in 0. So 0 minus 2 is equal to negative 2. So our point, sorry, I ran out of space. Our point is 0, negative 2. Okay? So 0, negative 2. Well, here's 0, and here's negative 2. Connect it. And our arrow faces away from the wall. Okay? Okay, so just a couple of quick notes here. On your walls, you have open and closed dots. One dot will be open, one dot will be closed. That is the only place where you will have an open dot. All other dots are closed. So this is sometimes a source of confusion, so I'm just going to write it down. Open dots only exist on walls. Okay? Arrows always face away from the wall. You don't want to indicate that the function is going through the wall. Okay? And you do one function at a time. You only need 2 points because it's a line, and you only need 2 points to make a line. Okay? So this is a 2-piece function. Okay? And it doesn't, notice the examples I drew, it was always connected. This is not connected. That's fine. It doesn't have to be connected. It will not always be connected. We just call this a discontinuous function. That's all. Okay, let's do one last example and then we're done. So you can, once I put the function up here, you can pause it, you can do it on your own, and then just check the graph, make sure that you did it correctly. This takes some practice, okay? So take it slowly. So we'll do 3 pieces this time. So let's just do x. For x is less than or equal to -3. Then we'll do -2x minus 3 for -3 less than x less than 2. Okay, so in other words, the first function is when x is less than or equal to -3. The second function is between -3 and 2. And the third function is, let's do 3x minus 2. And that's for all x greater than or equal to 2. Okay, so let's graph it. So first of all, we're going to find our walls. It's 3 functions, which means that we have 2 walls. X equals -3 and x equals 2. So our walls come from these numbers here. Okay, that's how we know where our walls are. So let's start a graph. And I'll try and be cognizant of space. So we have a wall at -3. And we have a wall at 2. Again, these dashed lines are there only to guide us, okay? Now we're going to graph the top function. So we always have to plug in the wall. So we start by plugging in x equals -3. So at x equals -3, we have -3, right? -3 is just equal to -3. So our point is -3, -3. And because it's a wall, we have to figure out, is it open or closed? So at -3, it's closed because there's an equal sign. It's included. You will only have to do this on walls. Okay? Then you're going to plug in a second point. So it could be any point that's less than or equal to -3. So let's do x equals -5 and -5 equals -5. So our point is -5, -5. Okay, so keep that in mind, that you only have to worry about closed or open on the walls. And for every single function, you're going to be plugging in whatever their walls are. Okay, so we have 2 points on this function. We have -3, -3, and -5, -5. So -3, -3 is a closed dot. Then we have -5, -5. Remember, everything is closed when it's not on the wall. And our arrow points away from the wall. Okay, next function. This is our middle function. Let's do this one in green. Notice I'm doing each one in a different color. I do that just so that it's clear to you which function is which and what we're working on. So 3, we graph the middle function. And the middle function is always kind of nice because you're already given the 2 points that you need to graph. Right? Because we have 2 walls. So we have to graph x equals 3 and x equals negative 2. And x equals 2. So at x equals negative 3, negative 2 times negative 3 minus 3. This gives us 6 minus 3, or 3. So our point is negative 3, 3. Okay, so we got the negative 3 from here. We're plugging in one wall. We're working on the middle function. We get that our y is 3, so our point is negative 3, 3. And we have to decide, it's a wall, so we have to decide, is it open or closed? And it turns out that this one is open. There is no equal sign. It's not included. And we do the second point, the second wall. So our second wall is x equals 2. So negative 2 times 2 minus 3. This gives us negative 4 minus 3, or negative 7. So our point is 2, negative 7. And again, this is on a wall, so we have to figure out, is it open or closed? And this one is also open. There's no equal sign. So we could plot it. So let's just put in the extra numbers. So this is negative 7 down here. And then we also have to go up to 3. Okay, so we're going to have a point at negative 3, 3, and that's going to be an open dot. And we're going to have a point at 2, negative 7, also an open dot. And we just connect these. And we don't have to worry about an arrow because it's between 2 walls, so it doesn't keep going in any direction. So this is the middle function. And finally, let's do the bottom function. So let's do that in pink. Notice our process is the same for every single function. We graph the wall, we graph another point. If there isn't another wall, if there is a second wall, like in the middle function, then we have the 2 points are both walls. So the first thing that we do is plot the wall, right? We're plugging in x equals 2. So 3 times 2 minus 2, 6 minus 2, or 4. So our point, it's 2, 4, right? X value is 2, y value is 4. And is it open or closed? It's closed because there's an equal sign. Okay, and we just choose another point. It has to be greater than or equal to 2. Let's choose 3 just because we don't have a lot of space on our graph. 3 times 3 minus 2 gives us 9 minus 2, which is 7. So our point is 3, 7. And remember, if it's not a wall, then there's no question. It's always closed. So we're going to go in and we're just going to add the numbers that we need here. 4, 5, 6, 7. And here's 3. So we have the point 2, 4. 2, 4 is a closed dot. And then we have the point 3, 7, also closed dot, connect, and our arrow faces away from the wall. So notice every single wall has an open dot and a closed dot. These are all things to help you figure out, hey, something went wrong. Okay, and that's it. So we have an open dot, a closed dot, an open dot, a closed dot. We have a line in every single section. You should see a line in every section. Most likely they will not be connected. It's not impossible that they are. Okay. The arrows face away from the walls. The middle function has no arrows because it's running between two walls. Okay. And x means positive slope. This has a positive slope. As we go to the right, we go up. Negative 2x minus 3, negative slope. This has a negative slope. As we go to the right, we go down. And 3x minus 2, positive slope. As we go to the right, we go up. So you can tell, hey, we're on the right track because we have a line with positive slope, a line with a negative slope, and then a line with positive slope. So even if the numbers aren't quite right, or you don't know if they're quite right, you know that you did something correctly. Okay? Whereas if the slopes don't match, then you know something went wrong. So that would be the first thing that you would look at to say, these are things that you're going to look at to say, oh, did I do this correctly? Is there a good chance that I got it right? Do I have an open dot and a closed dot on each wall? Yes. Do I have 3 separate linear functions? Yes. Is my first function positive slope? Yes. My second function, negative slope? Yes. My third function, positive slope? Yes. Okay, that tells you you're most likely correct here. Okay, so it means that you could look at your graph and say, it looks reasonable. And that's it. So that is graphing piecewise functions. I'm sorry, this video also turned out pretty long, but take breaks in these videos. Okay, there's nothing wrong with taking a break. That's it.